complex integral, and notice that it has a nice natural curl equation in there. Who remembers the curl equation? So if the curl, let me remind you of a curl of vector field PQ. What was the curl of vector field PQ? Inside the Green's theorem, right? How does it look like? Qx minus Py. That was the curl. And if that's 0, we have a nice equation. So some partial minus some partial 0. So what comes to your mind by looking at this complex analytic function? And then when I asked this question first, nobody answered it. Maybe this time I'm going to answer. I'm looking at the complex analytic function there. I'm looking at some curl equation. How do you make this two connection? What curl are we talking about here in this? Vx minus uy. Isn't that right? Is that right? Ux minus, I think I did it wrong. The Vx plus ui. Right? Ux is Vy. Right? That's a Cauchy-Riemann equation. So if we look at it here, Cauchy-Riemann equation, Ux Vx equals Vy ui. 90-degree rotation backwards. So Vx plus ui will be 0. Is that right? Yeah. And the top one, ux minus vy, is going to be 0. All right? So why did I write this one? Cauchy-Riemann equation is curl 0 condition. These are the two variable functions, right? So it seems like a curl 0. So what vector field are we associating in here with that curl? So if you're looking at the curl, you have to swap this q and p back into place, right? So this is x place and y place in here. So u goes back there, right? But when this one, y part, when is going back to its place, is flip the sign. So it must be negative. And this one going back to the y place without the partial. So if I call that vector field f, what is the curl of this vector field? 0, right? That's what we're looking at. Let's look at next one. How about this one? I'm going to call that vector field a g. How do you go back from the curl? You swap, v is going back to its x place, but it had already negative there, so this is all right, like that. Correct? All right. For some reason, if you flip the sign, flipping the sign doesn't really matter if you can put the negative in there. So instead of that, using u minus v is more natural to complex analytic function. Is that okay? If curl of f is 0, curl of negative f is also 0. The negative multiplier doesn't do anything. So rather, we're going to use this version and that version. Okay. So what do we have from there? Curl 0 implies something about line integral, right? By Green's theorem 1, what does that mean? Green's theorem 1 requires what? Not curl 0. Green's theorem 1 requires what? Forgot to record from here. So according to Green's theorem, you apply this vector field of Green's theorem. So we have this x part component, y component in there. Green's theorem says double integral, right? Over the region. So I have to do this again. I was wrong about this. It should be d in there. Sorry about this. I'm changing to d, and that's the region d there with a boundary, simply connected region. And that becomes region d, right? So we're going back to curl. We already know the curl, right? What is the curl of this u minus v? 0. That's how we started in here, into 0 dA. Okay. So what is the two adjectives that are connected in here? Curl equals 0 for vector field. here, what is the adjective for the function f? Analytic, right? Analytic gives you CRE. CRE is interpreted as a curl 0. That's the situation, right? So make sure you understand this connection. All the thing we've been doing in terms of real geometry was a curl equals 0, right? What was that again? Here is interpreted as analytic, right? Analytic CRE, that's a curl 0. That's why we're using it here. So, so that's 0. So let's do one more. In the same region, an arbitrary simply connected region, and what is the other curl condition we have in here? This is it. It's this v dx plus u dy. Is that right? And that's also curl 0 here. V and u are x component and y component. These are p and q. So what happened to that? Curl this time? It's something different, right? So what happened to the curl this time? I want to make sure that you're looking at the right thing. It's a 0. Okay. So what is the meaning of this calculation again? Who started this business? Physicists, right? Physicists started business to calculate what? Vector fields, word calculation, right? So I'm going to give you an interpretation in here. Here's a point, z0. And remember there was a codomain plane and domain plane, that picture? Remember that? This time, this is a domain, and there's no codomain. No codomain. All right? Then I'm going to use u minus v as what? I have a point in here, and physicists will look at it as I'm going to collect this u and minus v and make it into what? Vector field, right? Vector field. So here's a vector field. Maybe there's a u and minus v right there. But it's really a complex number, u minus iv, right? Now, we're not interpreting complex number as a position, like in the codomain. This time we're interpreting complex number as a directional vector there, right? Okay, yeah. So what is a good name in the relation between u plus iv and u minus iv? Anybody remember that? U plus iv versus u minus iv? That's what we're looking at here, u minus iv. Originally we started with u plus iv, right? What is u minus iv? Complex conjugate, right? So the other one is a vu. The other one is a vu. So I'm going to plot that vector as well. What is the relationship between these two vectors? U minus v versus v and v and u. First of all, u and v are swapped, right? And one of the thing switched the sign. Remember that? U and v are swapped, and one of the thing is to switch the sign. What is the relationship between these two vectors? Great, got it, perpendicular. The question is that forward 90 degree or backward 90 degree? You can experiment, because there's one answer you can play with 1, 0, and 0, 1. This time, turns out it's a forward. All right? Forward, you flip that to backward and change the sign and up there. Makes it positive right there. That's VU, and that's 90 degree rotation. So there's two vector fields associated in here, but it's not arbitrary, this 90 degree rotation forward. So there's one vector field, and there's another vector field in there. So there's a curve. Maybe that's a part of arbitrary shape of D in there. So if you do this calculation, both of them becoming 0. Correct? Doesn't matter what D, region D or curve is, as long as you stay inside this region, this is always a 0. Right? So this vector field F, which is u minus v, vector field G, which is v and u. If this integral is 0 all the time, anybody remember this one? Are what kind of property? The three properties, right? Parametric independence and those things. So what does that mean here? Integral is always 0. Orientation dependence, right? What was the third one? Path independence, right? It means in that analytic region there, if you go from here to there, doesn't matter how you get to that, the vector field integration of this one is going to be always the same. All right? So it's not too arbitrary again. It is somewhat related nicely like this. So we're going to combine this one together, and that's the next bit. We're going to combine it into one integral using complex structure, just like Euler's formula, just like real the derivative in the Jacobian level. All right, here is the thing. The idea is the following. I'm going to draw this horizontal line. If you look at the first one, is when you actually calculate with the parameterization, you're dealing with this one, right? U dx minus v dy is a shorthand notation of u dx dt minus v dy dt, right? Why did they remove the dt? Anybody remember why they could remove this dt? So it doesn't matter how you parameterize it, so they don't care about this dt, so they will just write it like that. And that's 0. Whilst the other one is a v dx dt plus u dy dt is 0. All right. So it is not easy to come up with. And how do you combine this one nicely into one complex? There's no complex here, right? Everything is real. So some people realize that, hey, that really comes from the following. It's a pretend motivation. You actually do it backwards. So let's see what happened if you multiplied it out. You get u dx dt, right? For the real part. Correct? If you multiply these two, ux dt. But if you multiply the other two, you get negative v dy dt. That's the real part of the product of these two complex numbers. Make sense? How about the other one? I times v dx dy, dx dt, I'm sorry, and u dy dt. Okay? These two separate quantities, real quantities, shows up as real and imaginary part of a product of two complex numbers. Okay? So that's going to be what kind of complex number? 0 complex number, because the real part is 0 and the imaginary part is 0. Right? Okay, so let's rewrite this phenomenon. What is the name of u plus iv originally? That was a complex function, analytic complex function, right? Right there? So I'm going to rewrite it. We're looking at some analytic complex function, f of z, and z is eventually parameterized with respect to real variable t, but is multiplied by that vector in here, dx dt. So let me write it like this. X plus yi is a z, right? That's what this z is representing. And x and y are parameterized with respect to real variable t. And this can be denoted as dz dt in that way. dz dt equals 0. So those two quantities, nicely related, is now have a compact notation. Fz times is not dot product, is a complex multiplication. dz dt equals 0. Okay? Does that make sense? It's easy to prove that one equals that. It's difficult to notice that kind of thing. Any questions so far? Let me just give you one remark is a little clarification. ddt versus ddz. Okay? T is a real number. So when you're differentiating complex number with respect to real number, it's just like differentiate this one and differentiate that one. That's it. If you really apply the derivative definition with the t, the real value only, and that's it. But what's different about this ddz? Remember whole definition. This is the Jacobian level. That's exactly what you're going to get. It's a Jacobian level, right? But what one more thing you do when you do the complex differentiation. Remember that two Jacobian tangent vectors? What is the last bit you do with that mu thing? If you remember that trigger. Taking rotation back 90 degree, right? That's one thing involved. And what about this one? ddt is missing that one, right? Therefore, it gives you all different directional derivatives. Okay? So that's what we're doing. There are complex numbers there, but we are differentiating with respect to real variable dt. So it's not complicated. Just real part differentiated and imaginary part differentiated. So I'm just using your intuition to make sense out of this ddt done to the complex numbers, complex function. Is that okay? All right, good. So that's the situation there, and we have that. So we have this phenomenon right here, and this triggers this definition. Let me further state this so that this definition makes more sense to you. Okay. So this is important observation. F of z times dz dt is going to be, wait a second, I'm continuing. So you have u plus iv and then x plus iy, and they're all parameterized with respect to t. Formally, if you just expand it, you can imagine there is a real part that has all t in it, and you collected imaginary part, collect t in there, right? And that's exactly what that g and h is. Okay? The whole reason we consider all this thing is a phenomenon that if you integrate this ab to gt dt, and if you integrate ab to this ht part, what will those integral of this one from a to b and a to b if it is still coming from that situation there? Is all 0, right? If it is about the closed curve, starting t equals a, coming back to as t equals b, same point, and then this is representing real part of a curl of something. By Green's theorem, you have a 0, and that part is also 0. Okay? So what you're looking at is very compact notation here. Fz times dz dt actually have a real part and imaginary part, and integral of the real part is 0. Integral of the imaginary part is 0 if it is parameterizing a simple closed curve. Okay? Yeah. So that's the magic behind this one. Complex analytic function, compose it with a t, separate a real part and imaginary part, each integral becomes 0. So here's the definition. So why don't we define number 1, a to b, doesn't matter if it's simply closed or not, a to b of this complex numbers, ht, dt. Separately, this one and plus that one. So make this one as a definition. We're going to integrate this one first. Plus, we're going to integrate that one. This makes perfect sense. Everything is real integration. And then we're going to put outside I in there. As if we're treating I as a constant, real constant, right? If I is a real constant multiple, then you can factor out like this, right? but it makes no sense. It's not real integral, so we're defining it. Algebraically plausible that obeys the nice integral laws. Okay? So consequence of this is applying to that. And here, if you have simple closed curve C with the parameterization x equals xt, y equals yt. Okay? Then according to that parameterization AB, and we're looking at complex analytic function times dz dt, which is a complex multiplication with xt and yt in there, and dt. So like that. So complex analytic function, stick in all the t's in there, multiply by dz dt, and you separate the real part and the imaginary part like that. And this whole thing has meaning, right? Okay. Do you know the answer to this one? Right? Because the real part and the imaginary part is going to be 0. Okay? But if you separate this one, and this is a stage, and I have to introduce this one. Behind it, what we have is this vector integral behind it, u minus v and vu, right? That's behind this compact notation. Okay? So that's the line integral of what kind of object? What is behind it here is a line integral of two vector fields, right? So that's a parametric independence because of what's involved in here is parametrization independence, correct? So this one is also parametrization independence. Doesn't matter how you parameterize this curve C you're looking at, you're going to end up at exactly the same result, the 0 in there. And if it is not the 0, if you're just looking at non-analytic function, it is the definition behind it is still vector field integration is a parametrization independence. Okay? It's analytic. Let me emphasize it here. If f is not analytic, or if it is not in simply connected region, this one, parenthesis, so, I'm being careful that you can't just cancel this dt. This is just definition and notation I'm introducing. This is still parametric independence. Can somebody explain again why this one is a parametric parametrization independence? I'm using the wrong words. Parametrization independence. It's coming from this structure. This is exactly dot product of vector field to tangent vector, right? So it's a line integral of vector field. Therefore, it's a parametrization independence. Okay? It has nothing to do with this thing being 0. That's what I'm stating separately. This definition itself is a parameterization independence. Okay? So, number 2 is a new definition here, is that if you have curve gamma, not necessarily closed, the curve gamma, fc dz. So here, it is not about canceling these dt. I want you to look at it the same thing, and a p dx and p dy, that, let me introduce that notation there. Where did I do that? Here, right? So why didn't I write this dt in here? Because it was a parametrization independence, right? So that's the definition of this notation. I'm doing the same thing. Because these guys are parameterization independence, I'm just going to lose that t and just write down the object. However you parameterize it, it's going to be the same. Okay? So that's the definition, is that you parameterize it and stick it in there and replace the dz with the dt and integrate it for any parameterization. Anything that is convenient. Any parameterization doesn't mean that you can use a different circle. It's the same circle, just parameterized differently. Does that make sense? Okay. So that's the definition. I have time for one example. Sorry about that. So here's an example. C, we're parameterizing of complex number 1 over dz, 1 over z dz. And C is the circle of radius 1, or radius r, not 1. All right. We're about to calculating this integral, and somebody come up with this parameterization, z. Very compact parameterization. Not using cosine t and sine t. How would you parameterize this complex number nicely? Radius r and a circle. R times e to the it, that which is cosine t in it, so t is in there. All right, that's one parameterization, right? So we're going to use it. By definition, what is it? It changes from where to where? The C curve is parameterized beginning t equals 0, 2 pi. It could be negative pi to pi. However you parameterize, you will end up at the same answer, right? Okay. How about 1 over z? Z is now this one, right? Parameterized version. R is not changing. E to the it. Correct? Now dz dt and times dt. So here, r is a constant. Only t is a variable. You can just use a chain rule in here to differentiate it. So r is a constant multiple, right? What is the derivative of e to the z? E to the it, right? And multiply by derivative of it, chain rule, right? So it's I. So if you really break it down, this makes perfect sense. This is how it works. So how does it simplify in there? R cancels. You see that? E to the it cancels. And only I is left. It's constant I, and from 0 to 2 pi. And dt. In the very first definition, you can treat this I as a constant multiple. Just like that's the beginning of the definition. So I goes outside. 1 dt 0 to 2 pi. Is that right? So what is it? 2 pi I. So that's the answer to that. Do you know what that means? If you break this one about the real part and imaginary part, if you do that line integral of each individual part, then you will get one part 0, an imaginary part, and 2 pi. That's what that means. We're going to continue with this one. I guess it's going to be largely review of this lecture, and